etc. So this talks about a paper that came out a few months ago with Scott Collier, who's a grad student at Harvard, and Jan Gobet, who's a student at McGill, and Henry Maxfield, who's a KITP as a postdoc. And the idea is to A, generalize the light cone bootstrap story in D dimensions to 2 dimensions, where it breaks down, for reasons I'll explain if you're not familiar. And B, to translate this into statements about 3D gravity, and in particular, statements about 3D quantum gravity, because our results will hold at finite C, and using basic elements of ADS-CFT dictionary, we'll learn about the bound state spectrum of 3D gravity. So let me actually just write the main result, in a sense. And this result will be an exact expression for the purely gravitational contribution to the bound state spectrum of multi-particles in 3D gravity coupled to matter. So it's simple enough that I can write it down without introducing too much notation, and then the rest of the talk will be about explaining it. So in ADS 3, if we have, say, 2 scalars, coupled to gravity minimally, then we can try to compute the binding energy of some 2-particle bound states, and we let them interact gravitationally. So they exchange any number of gravitons, which schematically I can sort of draw like this. And in CFT language, this operator is dual to some double twist operator, O1, which is dual to phi 1. Say L derivatives and O2, and this is schematic, but this is a Virasoro primary in the CFT. And there are higher twist guys like this, but for the formula I'm going to write down here, let me just give you the lowest twist spin L 2-particle state. So if we just introduce a few definitions, then we can write down the answer. So if we define H to be the dimension minus a spin over 2, and we further define this in terms of some variables alpha and q, and alpha is just defined like this, and q will be defined in terms of g Newton, then the answer is the following. So the value of h for this 2-particle state is just h1 plus h2 plus delta h. And delta h is what we're trying to compute, and the answer is simply minus 2 alpha 1 alpha 2. And this is exact in the dimensions of 1 and 2 and the central charge. If you expand it in small g Newton, it has an expansion to all orders because of these quadratic relations. But in terms of alpha, it's a very simple thing. If you look at p-particle states, then the binding energy is just a sum of minus 2 times alpha I, alpha j, where I and j are summed over all numbers not equal to each other. So alpha 1, alpha 2 times plus alpha 1, alpha 3, etc. So far I'm making just a statement about a sort of pure gravity setup like this, where I don't have to make a large spin statement, but there will be a statement of large spin universality, which is that large spin bound states like this have twists which approach this value, even if there's lots of other stuff in the theory. Yeah. Okay, so let me give a sort of brief outline. First, I will talk about the light cone bootstrap and the structure of radial trajectories in CFTs in greater than 2 dimensions. Then I will explain why this fails in 2D, and so let's call this the 2D like on Bootstrap. Then I'll sort of translate into 3D quantum gravity language. So I'll sort of, talk a bit more about what this implies about the bulk and how you can make contact with some nice pictures in ADS. And finally, some applications of this result, which I'll phrase mostly in CFT language, which will include a few things. A formula for the cross-channel limit of Virasoro blocks, and a derivation of the late time behavior of the Virasoro blocks. And I think a couple other things if time permits. So I'm assuming that there's some familiarity with this sort of d greater than 2 subject, but there are people here, experts at various subfields of the topics of the workshop. So if you're not following, please interrupt me and ask a question. Okay, so let me draw a picture about what's going on in CFTs in greater than 2 dimensions based on an accumulation of work over the past several years. So I will make a plot of spin versus twist. And schematically, we know that CFT operator data can be organized into families, radius trajectories, which have the following basic shape. Okay. So this is a character, and I'll explain what parts are rigorous and what parts are not. So the statement is at large spin, every CFT has a sector of double twist operators which asymptote to mean field theory OPE data. So these are operators which are these double twists, which have spin L and twist n plus 2 delta phi, 2n plus 2 delta phi. So the dimension of these double twist operators in pure mean field theory is just this. And the statement is at large spin. Every CFT has operator trajectories which asymptote to these twists. So these are labeled by n, starting from 0 and going up. Now, as you perturb away from large spin, there's a large spin perturbation theory that can be systematically performed, which corrects these dimensions by some anomalous dimension. And the universality is the statement that at large spin, this decays like the spin to the minus tau star, where tau star is the twist of the lowest twist operator appearing in the OPE of the external operators O. This can be corrected in powers of 1 over spin, and then subsequent powers of the spin suppressed by the twist of subleading twist operators in this OPE. So you can get this kind of operator by operator correction to the large spin MFT data in this way. Now at finite spin, we now know that there is an analyticity in spin of OPE data. So these large spin trajectories can indeed be completed to finite spin trajectories, by which I mean that operators of physical operators in a CFT of some integer spin can be taken to sit at points on these trajectories which interpolate between the set of physical operators, physical local operators. So let's say if you're spin 2, then the leading trajectory always includes the stress tensor at twist d minus 2. And at higher integer spins, there are some other guys here. And the interpolating operators are light ray operators. You can talk to Peter about this. But from the perspective of the large spin story, this is about the notion that you can actually non-perturbatively complete the large spin expansion into some set of families which exist at finite spin. There's an asterisk here, which is that the analyticity extends only down to some low spin. Non-perturbatively, that spin is 1. So here, in this region, there's some sort of non-universal, non-analytic contributions that might be present in any given CFT. Okay. So, any questions about this? Okay. I've drawn all these trajectories as if they're convex. Only the leading one is always convex. The higher trajectories are not necessarily convex, but you have to draw a picture, and this gets the point across. I should also say that there are also other trajectories in principle that might asymptote to something which is not mean field theory at large spin, but the statement is that the OP coefficients of those trajectories decay faster than this. So in that sense, at large spin, the dominant operators are these. So yeah, I mean, I'm trying not to take a large n limit, but right. So in large n theories, we have large spin operators, which might be these dual spinning strings, for example. That's even a little tricky because their spins grow logarithmically. So at large spin, they, at infinite spin, they strictly decouple. Actually, understanding what happens to those operators at finite n, I'm sort of curious, actually. But yeah. But for example, you also have not just double twists, but higher multi-twists, and those trajectories, inside the OOOPE, those trajectories are subleading at large spin compared to these. So at the very least, you have those. Okay, so the philosophy of studying this data that I like now, and this is partly based on work from August with Vladimir Rosenhaus, David Simmons-Duffin, and Junyu Liu, is that you can analyze these contributions operator by operator, and that the crossing, the data for these double twists is nicely packaged into the crossing kernel for conformal partial waves. So one of the messages that I'm going to use is that the crossing kernel nicely packages all this double twist data into one object. So why is that? So if we think about a t-channel exchange in our 4-point function of O's by some operator O prime, then if we decompose it into the S channel, say as a sum over spins, and write it as some formal contour integral over dimensions, then we decompose this into some set of exchanges here, times some overlap between the t-channel partial wave and the S-channel partial wave that we're interested in. And this thing is the crossing kernel. And when you try to make this formally well-defined, these operators should all be in the principal series of the conformal group. I can talk more about that if people would like, but often the statements we'll infer from this will just be analytic continuations away from that series. So having said that, this thing, the crossing kernel, the overlap of S and T channel partial waves, has poles in the delta plane. Poles at delta equals the dimensions of MFT. And so if delta prime, the dimension of the T-channel operator, is 0, these are simple poles. And if the T-channel operator is not the unit operator, then these are double poles. The residues of these simple poles just give you the MFT OPE coefficients. And the residues of the coefficients of the double and single poles here give corrections to those dimensions, namely this, due to the exchange of a given T-channel operator. So you can think of this total anomalous dimension as a sum of contributions from T-channel operators. At large spin, they're ordered by the twist of the T-channel operators, but at finite spin, you just add them all together. And each such contribution is encoded as a double pole of this crossing kernel, given some T-channel twist of O prime. So in other words, gamma NL is like a sum over O prime of gamma NL due to T-channel exchange of O prime. And this thing is what's encoded in the poles and residues of this object. Yeah. Yeah, so that's correct. So this is sort of schematic. Right, so if you're interested in some large spin expansion, then this is fine to think in this way. But I truly... Yeah, no, it's true. I mean, I'm assuming basically throughout the talk that there's no small parameter in the game. And if there is, then sometimes funny things can happen. You mean double twist, large spin, double twists? Yeah. Well, sorry, but those in general, for generic dimension of O, those will not be degenerate with the 1 over L to the 4th correction, say. I mean, sorry, those operators do, but it's true. So at large spin, you have this degenerate tower, indeed. So you can compute the self-corrections from that. And that actually has not been totally worked out. Sure, I mean, yeah, not totally. So yeah, that is true. So let me put 2 sets of quotes around this sum. Yeah, in a full CFT, that's correct. Of course, there are many situations that are interesting where you have some finite set of operators whose contributions you're curious about. Large N, for instance. Yeah, thanks for the comment. Okay. So in the work from August, we studied this object, following up on work in 1 dimension, say by Matthias and Bolt, and some work by Abhijit Gade. And you can compute this crossing kernel, which is equivalent essentially to the 6J symbol of the conformal group, and we computed it in some low dimensions. This talk's not about that, but I'm happy to discuss it. So now let's go to CFT2. Okay. Good. So in CFT2, the large spin expansion breaks down because you have an infinite tower of, from the global conformal perspective, conserved currents which have twist 0 because you're in 2 dimensions. When you have twist 0, the large spin asymptotics are constant, naively, and so it's not clear how to order this problem even in the large spin expansion. So no twist gap from the perspective of the global conformal symmetry. So you have the stress tensor, and you have the stress tensor squared. Any number of composites of the stress tensor has twist 0. So you have to resum some infinite tower, which is to say you have to account for the entire Virasoro vacuum module to ask what happens to, say, the MFT asymptotics at large spin. So that's what we're going to do. And the philosophy is to study the crossing kernel for the Virasoro blocks instead of the global blocks. And the poles of the Virasoro crossing kernel will tell us, rather the support of the Virasoro crossing kernel will tell us where the sort of large spin operators sit, and the residues tell us the OP coefficients and anomalous dimensions. Okay. So now let's set up some notation. So we're going to look at a pairwise identical correlator, and we can sum this in the S channel, which in my conventions is going to be 1, 2 goes to 1, 2. The Virasoro blocks curly F in the S channel will be a function of the momentum alpha of the S channel exchanged operator. And so let me make, actually let me put that up there. Let me make a box of definitions which we will need throughout the talk in case these variables are a little less familiar. So we're going to define H to be alpha times Q minus alpha, and Q to be B plus B inverse, and C to be 1 plus 6 Q squared. So for some central charge, you can specify alpha, the momentum, instead of H, the left-moving conformal weight. And you might be familiar with this parameterization if you've studied Liouville or Coulomb gas or linear dilaton in 2D. And it's interesting that this parameterization is very useful for what I'm about to say, which applies to all 2D CFTs and doesn't have anything to do a priori with, say, Liouville. So good. So we have this S-channel expansion. We can also expand in the T-channel. And as you can see from the definition up there, there are two natural ranges of dimensions. One of them I'll call the discrete, for reasons that will hopefully become clear soon, which corresponds to H bounded below by 0 and bounded above by C minus 1 over 24. And in terms of the momentum, this is the range of real alpha bounded above by Q over 2, which is just algebra. There are also some continuum states, which are just H greater than or equal to C minus 1 over 24. And in this case, the momentum alpha is complex, equals Q over 2 plus I times some real number. So in 2 dimensions, holomorphic factorization means that these double twist operators in general split into a chiral and anti-chiral piece. So we can think of this as like, so let's see, we have an O1, O2 double twist operator labeled by N and L. And so we can think of there being some holomorphic piece and some anti-holomorphic piece, each labeled by non-negative integers, M and M bar. And you can think of this as like O1, D to the M, O2, where this is the holomorphic derivative. And this has H equals H1 plus H2 plus M. And likewise for this antichiral piece. N is just the minimum of M and M bar, and the spin is just the mod of the difference of the two. Yes. Sorry, can you say it from the beginning? Oh, no, so I mean, if you just, I'm just saying, imagine studying ordinary mean field theory in 2D, then you can split them in this way. And now we can ask about incorporating finite central charge. Yeah. So for a lot of the talk, I'll be referring just to the holomorphic piece. Not always, but just when I do that, keep in mind that there's always this split into 2, as usual in 2 dimensions. Good. So the T-channel block can be written in terms of S-channel blocks, and we'll write it as an integral over S-channel momenta times this S of alpha S alpha T. Now this is what I'm calling the kernel. It's called S for historical reasons, but that's the Virasoro crossing kernel. And this expression is an integral over some contour in momentum space. In particular, C is an integral over the continuous part of the spectrum. So you take a single Virasoro block, you invert it, and you get an integral over continuum blocks in the cross channel. So as a result of this expression, the point that I want to get across is that you should think of the holomorphic and anti-holomorphic kernels multiplied together as the S-channel spectral density, or OPE spectral density. I'll just call that spectral density for short, due to some T-channel operator OT. Okay. Now, before we proceed, this kernel was computed by Ponceau and Teschner, and it was computed in a seemingly different context of as a 6J symbol for this quantum group, which has some representations in common with Virasoro, but is not itself Virasoro. The fact that it actually is the Virasoro crossing kernel is sort of confusing, and we're going to, it has in the past passed some checks, but I should say that it's still somewhat mysterious to me, but we're going to do some calculations with it, and it'll pass every check that we subject it to. Formally, as in the case of global conformal blocks, this kernel is only well defined when the blocks are living in the continuum set of representations. So we're going to analytically continue away from that, which you have to do, for example, if you want to study operators in this range, which, say, a large C is something that we often want to do. But we'll be careful about it, and then a lot of the interesting results we get will arise from this kind of analytic continuation. Okay, so good. So in line with our philosophy from before, we want to understand what the support is of this kernel, and of course that's already contained in this equation. It's supported on this continuum. But let's look a little more carefully at the consequences of that. So the analytic structure of the kernel, well, it's a pretty complicated function, but for us, for the sake of this discussion, all we need to know are the fact that it's meromorphic and to know where its poles are. Okay, so it's a meromorphic function with poles at alpha s equals alpha 1 plus alpha 2 plus mb plus nb inverse, where m and n are non-negative integers. It has poles here, and at its reflections, which means that I take all the alphas and I take them to q minus alpha. So alpha 1 and alpha 2 are the momenta of the external operators. So the statement is similar to the crossing kernel in the global case. For any T-channel exchange, we have poles at the same S-channel locations, which are just fixed by the external momenta, not the internal T-channel momentum. The residues will depend on that, but the location of the poles is independent of that. And analogous to the global crossing kernel, when alpha t is 0, which is to say the T-channel exchange of the unit operator, so the Virasoro vacuum block in the T-channel, gives a crossing kernel which has only simple poles. And when alpha t is non-zero, there are double poles. So there's a nice analogy forming here, and maybe you can already see your way to the end. Yes, you can't write it solely in terms of those, but you can write it in terms of this this Barnes double gamma and things made out of that. It's basically just that. So S is written as a product of these Barnes gamma functions times an integral over more ratios of these deformed gamma functions. So S itself has an integral representation for arbitrary alpha t, which, as far as I know, can't be simplified any further. If you look at the vacuum crossing kernel, then actually you can do the contour integral, which defines S, and write it just as a product of these deformed gammas. But that is the set of functions that is appearing. Okay, so let's sort of draw a plot which puts these things together and will give us the answer we want. So if we first take alpha 1 and alpha 2 in the continuum, then we can make a plot here in alpha S space. So the contour C runs along here. Right, this is the contour that defines the inversion of the T-channel block. And we said that this S has poles at these locations, and when alpha 1 and alpha 2 are in the continuum, their sum is P plus I times a real number. And so you have a bunch of poles in alpha space here, and there's sort of a few different sets of poles that are related by reflections. And so, noting that this is a plot in alpha space, not in H space, so sorry, this is Q. This is an integral over a continuous set of unitary representations where H is C minus 1 over 24 and up. So the answer for where this has support is just the continuum in the case when the external operators are heavy enough. You should resist the temptation to deform the contour and pick up the poles because they would give you imaginary values of H. So this is the answer in the form that we wanted. On the other hand, now you imagine decreasing alpha 1 and alpha 2. So suppose that they're not in the continuum anymore, but they become part of the discrete spectrum. So let's say alpha becomes just real and becomes, say, we take it to be Q over 2, and then we start decreasing. Then eventually some of these poles will cross the contour, right? Because this is at real alpha equals Q over 2. So first they'll move toward the real axis, and then they'll start going like this. Let me just keep them separated for the sake of illustration. And eventually some of them will cross. And you're going to pick up some discrete set of residues. So this happens when alpha 1 plus alpha 2 becomes less than Q over 2. Right, so they're both real, and then they cross this line. And so you pick up these poles. So you have discrete representation poles. And so this equation gets supplemented by a finite sum over some number of poles. So in particular, these poles are at alpha equals alpha m, which we define to be alpha 1 plus alpha 2 plus mb, where m equals 0, 1, dot, 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 such that alpha m is always less than Q over 2, such that these poles are to the left. That's right, yeah. But just for the drawing, it's better this way. So there's some finite number of these discrete poles. You might be wondering, where did the NB inverse go? So I should have said that this definition is invariant under B goes to B inverse. So without loss of generality, you can set B to be between 0 and 1. This covers all central charges greater than or equal to 25. And if you want to go between 1 and 25, you take B to be a pure phase. Let's just ignore that region for now. So when B is less than 1, these poles at non-zero values of n are always to the right of the contour, because B inverse is greater than, which is of order Q, and Q is greater than Q over 2. Okay. So in any case, you have this finite number of discrete poles at this finite set of alphas. And so if you write the T-channel block in terms of S-channel blocks, you have this continuous piece. Plus, or rather minus, 2 pi times the residue at alpha equals alpha m, the sum over m over this range, of the kernel times the block. Okay. This set of discrete poles, just to emphasize, arises when the external operators are sufficiently light with respect to the central charge. Okay, so that's the sort of technical part of what the crossing kernel tells us. But this is all we need to interpret the 2D analog of the light cone bootstrap. Any questions? That is the most technical part of the talk. The rest will be understanding the consequences of this. And I should say I was pretty fortunate that this kernel had been computed before, because that really would have been the most technical part of the talk. It's like an insane object. Okay, so let's start with vacuum inversion. So in other words, we take the T-channel operator to be the identity. So we're going to study the kernel where the T-channel guy is a unit operator. And let's draw an analogy, just to be completely explicit. In MFT, we have these chiral guys, and they have H is just the engineering dimension, and M is just a non-negative integer. The vacuum inversion leads us to define something that we'll call Virasoro mean field theory, or VMFT, which is generated by some sort of objects I'll put in curly brackets, which are like the sort of Virasoro version of these double twists. And they have momentum alpha m equals alpha 1 plus alpha 2 plus mb. And m is bounded above by this value such that the poles no longer cross the contour. Okay. So in mean field theory, the dimensions add, and there's an infinite tower of operators. In Virasoro mean field theory, the momenta add with this funny b factor, and there's only a finite number of these guys. And there's a discrete continuous piece. So let's make a plot of the central charge versus h of the operators in VMFT. So here we have the continuum boundary. And down here we have some discrete trajectories, which are functions of c. Turns out they look like this. At infinite central charge, you have an infinite tower. In our conventions, in terms of b, large c is small b, and the upper limit here goes to infinity. And so you have an infinite tower of discrete trajectories, and the continuum runs off to infinity, and you recover MFT. At any finite central charge, though, you have, say, like this, some finite number of these discrete trajectories plus this continuum. And if we simply translate this result for the momentum of these discrete states into a statement about an anomalous twist, then we get the version of the formula I showed you at the very beginning, generalized to arbitrary m. So this thing takes the following form: minus 2 alpha 1 plus mb, alpha 2 plus mb, plus m times m plus 1, b squared. And this is exact in b and alpha 1 and alpha 2. Right. So this is the result of just inverting the Virasoro vacuum block. At this stage, so the physical utility will be twofold. The first is that if you imagine coupling a theory of gravity very simply to some scalar fields, then this is the purely gravitational contribution to the binding energy. The other statement, which is what I'll show later, is that there's a large spin universality governed by VMFT in 2D CFTs. But indeed, there are a few reasons why VMFT is not itself a legitimate 2D CFT. The first is that it has a continuum, and we like our theories to be compact. The second is that when you combine left and right weights, the spin actually gets moved away from integers, because delta hm minus delta bar hm bar is in general not an integer. So when you have an infinite sum over operators that you invert, it must be such that the VMFT continuum is resolved and the spins return to being integers. This is an interesting constraint on the family of CFTs that realizes this, that I don't quite understand, but it seems like it could be powerful. Okay, so some comments, and then we'll move to the bulk, and then we'll write down some applications. So one of the applications I mentioned should actually be immediately clear for those of you who are versed in CFT2. So this whole thing comes from understanding how P-channel blocks are expressed in terms of S-channel blocks. So if you want to understand the cross-channel limit, right, that becomes trivial when you express it in terms of the other channel, and you just have to understand what is the leading twist block that appears in the cross-channel, because that gives you the leading singularity as z goes to, say, 0. And so that just follows from what I wrote over there. Okay, so some comments. The first is that H is independent of the spin. In other words, independent of m bar. And you can think of that as having come from resum an infinite set of global trajectories which are themselves spin independent. The reason that, say, the stress tensor contribution to double twist data is spin independent is that, well, it has 0 twist, so at large spin, it asymptotes to a constant. This is an analytic function of spin, and analytic functions that are constant in infinity are constant everywhere. So it's a constant function of spin, and you add up a bunch of things that are constant functions of spin, you get some other constant function of spin. That's the first comment. The second is that VMFT is not a good CFT. Well, we already talked about that. The third is that there's a form of non-perturbative unitarity encoded in this result, which is that this is always positive. So in a 1 over n expansion, then you see that for sufficiently large twist, the anomalous dimension becomes order 1 and can drive the total dimension negative. This tells you that you need further 1 over n corrections to unitarize the result. But here, this result is non-perturbative, and you can just check that for physical unitary dimensions, it's always positive. And finally, you can start forming a Fock space of multi-twist guys by taking, say, O1 to itself be a VMFT double twist composite. And when you do that, the p particle, in the discrete case, the p particle operator is sitting in momenta, which is just alpha 1 plus alpha 2 plus dot 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 plus alpha p plus mb. There's some degeneracy, but I'm not worrying about that right now. Okay. Maybe the fourth comment I'll make is that you might like to make contact with things that look a little more familiar. So if you consider the global limit, which is the limit of large central charge, which is b to 0, and h1 and h2 fixed, then you recover results from, say, single stress tensor exchange. So if you look at this result, let's just take m to be 0 for simplicity. Then we had minus 2 alpha 1 alpha 2. Now, in this limit where you keep the external dimensions fixed, it just so happens in this parameterization, this corresponds to taking alpha 1 and 2 to be of order b times h1. plus some correction, which is suppressed in small b. So you plug that into here, and you see that this goes like minus 2b squared h1 h2, which is minus 12 h1 h2 over c to leading order. And that's the result from single stress tensor exchange. If you expand this to whatever order you'd like in small b for fixed external dimensions, you start generating results for double, triple, multi-stress tensor exchange. And those results actually have never been derived from the global perspective. But of course, it's just very easy to expand this however much you want. Okay. Yes, yes. Completely, but I don't think it's a nice, simple result. No, so only in 2. Yeah, and maybe this is a good opportunity to state that this is all possible in 2 dimensions because the stress tensor forms a Virasoro subalgebra of the full operator algebra. So T only fuses onto T and its composites. In higher dimensions, this isn't true. So you can have TTO can be non-zero when O is not T or a composite of T. In 2 dimensions, this is not true. That's why the stress tensor dynamics are universal and can be resummed like this. In higher D, I mean, of course, it would be technically harder, but also it's non-universal in the sense that you get lots of other stuff, which is theory dependent. Okay, good. So the ADS3 interpretation. Yeah, absolutely. I'll get to that in a bit. They are at large spin, that's the statement, but I haven't shown that to you. Yeah. Yeah, maybe the better order would have been to go right into that, but I thought this would be a nicer place to stop and talk about gravity. So the sum of the left and right moving anomalous dimensions gives you the gravitational binding energy that we know from previous work, and so I'll just emphasize again that this is non-perturbative in G Newton. But there's a setting in which you can, in retrospect, have expected this result, which is to consider a massive particle which makes a conical defect. So in ADS3, a massive particle back reacts to make a conical defect with some angle theta. And this theta is, in terms of gravitational variables, given by this expression where m is the mass of the particle that back reacts to make the defect. Okay, so m you can think of as parametrizing this angle. And if we write it in terms of the variables I was using before, it's simply proportional to alpha. So the statement that, say you have this alpha 1 plus alpha 2 double twist composite is the statement that defect angles add. So if we had a composite of 2 defects, then the total angle is simply the sum of the 2, which looks natural enough when I draw it like this, but for a particle which is arbitrarily light, this is still true, and so this is a sort of quantum version of a statement like that, which makes sense classically. I should also say that this upper bound on alpha m reflects quantum gravitational back reaction, and in particular, so the statement that alpha m is bounded above by q over 2 is a statement that there's some threshold for black hole formation. I'm assuming scalar when I write this. Yeah, I'm assuming then you have a spinning defect, and the formula relating the angle with alpha is slightly different, and I can't remember off the top of my head, but yeah. So this statement is a bit puzzling because at large C, we understand that there's a black hole threshold starting at delta equals C minus 1 over 24. But at finite C, it's not clear. Well, I mean, we suspect that's still the black hole threshold, but there's less direct evidence for it. And certainly there's not a continuum of black holes above that dimension. So the fact that a continuum appears here somehow reflects some semi-classical black hole physics in the bulk, even though we haven't taken a large C limit. That's kind of confusing, but it's just a feature of the result, which I'd like to understand better. But I just want to point out also that this result here is not the same thing as the sum of the two dimensions being less than C minus 1 over 24, which is the naive statement about black hole formation. So, for example, if you take alpha 1 and alpha 2 to be equal, and equal to Q over 4, so as to saturate this, then this is the same thing as taking H1 and H2 equal to C minus 1 over 32, just by translating. So the sum of the two is C minus 1 over 16, which is naively above the threshold, but there's a negative binding energy, which brings it back down to sit exactly at the threshold. Okay. So now back to the CFD. Let's talk about what happens when you invert. Well, that was unfortunate. Let's see. Let's talk about what happens when you invert non-vacuum blocks. And this will be the statement of large spin universality that Joao was seeking. And that speaks to why this is relevant in general. Good. So now we want to perturb VMFT. We're just going to do this one operator at a time. So we're going to invert some T channel block for some non-vacuum Virasoro primary. And this will give us some anomalous momentum, alpha m, which depends on alpha t and alpha t bar. Okay. So this is given by some ratio of kernels. So this is given by C11t, C22t, times the ratio of the crossing kernel for T exchange divided by the crossing kernel for identity exchange. This subtracts out the VMFT anomalous OP coefficient, so we can just get right to the anomalous momentum. And there's a residue at alpha equals alpha m of the holomorphic kernels. Yeah, sure. Yep. Yep. Well, the statement I made about spin independence was just about the twist H, for one thing. So, yes. Yeah. I guess I find it confusing to think about requiring integer spin when we take a large spin. It kind of gets washed out, in the infinite spin limit, which is where this statement is supposed to be valid. I don't think that matters. So this is the expression for the anomalous momentum due to non-identity exchange. And it's controlled by this residue is some horrible thing. It's controlled by this ratio, which is an equally horrible thing. But now, if we think about large spin, we want to take large spin in the S channel. So we're looking at the large spin double twist operators of 1 and 2. So that means we take alpha S bar equals Q over 2 plus I P bar. And you take P bar, which is going to be of order root spin, to infinity. And when you do this, the statement of universality is that this ratio of kernels decays exponentially in the spin. So what that means is that any individual T-channel Virasoro primary operator only modifies the VMFT asymptotics by some exponentially small amount at large spin. This is an interesting contrast to the global case, where the large spin suppression is power law. Yeah. I wasn't going to, but we can talk after. Yeah. Yeah. So you can think of the global result as taking large C, so you're just decoupling the stress tensor, and then looking at large spin, and you get some power law. And here we're thinking about fixing C and taking large spin, so spin is much greater than C, and you get some exponential. And you can interpolate between the two by looking at L over C fixed as you take a large spin, and you get this cosh, which nicely interpolates between power law and exponential. Sure. Sorry, can you say that again? That feels like the answer would be no, because there just aren't poles of the crossing kernel at that location. I mean, the problem definitely splits into holomorphic times anti-holomorphic pieces, and spin only comes when we put the two together. So it's hard to justify that kind of motion away from integer m, because it would go against the properties of the holomorphic problem. But maybe there's a way to think about that, which is, yeah, I mean, maybe for some reason that's correct, even though it feels incorrect. Sure, yeah. Okay, so in the remaining little amount of time, I'll just mention some of the further applications of these results. So we already talked about a couple of them. One I'll just say in words, you can rederive the heavy, heavy, light, light blocks that Matt and friends derived sort of directly. So you can do this because it just so happens that when you express the T-channel block in the S-channel, there is a limit such that the S-channel block becomes a scaling block, and then you can integrate the scaling block against the kernel and reproduce the result. Maybe a newer thing is the cross-channel limit. So I'll just write it explicitly. So if we write the T-channel block, which is a function of, say, 1 minus z, as z goes to 0, then this is controlled. So here I'm going to assume that O1 and O2 are light. So in other words, they're in the discrete part of the spectrum. So there are these discrete poles in addition to the continuum, and the leading pole will give us the leading behavior at small z. So the behavior is z to the minus 2 alpha 1 alpha 2 times log z. This log is not there if it's the identity block. And so it's kind of nice. You see that this is the global behavior, and this is the augmentation when you include Virasoro. And this vanishes at large C because this thing goes like 1 over C. So you just get the global result back. So that's the statement about the cross-channel. And, well, I really don't have time to go into the statement about late times, but In the context of this ADS3 CFT2 information loss question, people have studied the late time behavior of these blocks, and that can be phrased as a statement about the cross-channel expansion. So you can go to the cross-channel and you encircle the branch point around 0 a bunch of times. That's equivalent to taking the late time limit of a T-channel block. And now that we can do that a bit more efficiently with this kernel, you can study this crossing relation in terms of the kernel. It's not on the board anymore. And just ask how this integral behaves at late time. It's a saddle point approximation. And ultimately, the statement is that viewing this as a function of t, which is related to the cross ratio in some simple way, this behaves like t to the minus 3/2, which was observed in some papers that looked at the zero blocks numerically. And so now you can prove that using the kernel at asymptotically late times. So there's no recurrence in particular. So there's no way that individual blocks can restore information in the sense that people had discussed. And so we can talk about that more later if you'd like. But anyway, that's the end. I feel like there's a lot more to do with this stuff. It's kind of a technology that has been somewhat harnessed in the Bootstrap context, but not completely. And so I'll just end there.